Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the first module of this course, that is the introduction module. And the idea behind this module is to give you a basic introduction to operating systems. So currently we are on the second topic, that is introduction to operating systems in this current module. And in this topic we are trying to understand what does the operating system do, right? So in the previous video, the first video, we said that the operating system is a special piece of software that manages the computer hardware, and it has two fundamental responsibilities, that is to make the computer hardware easy and efficient to use. So now what we are going to do, we are going to take each of the individual hardware components, that is the CPU, memory, IO devices, the storage devices. We are going to talk about each of these individually and see how the operating system manages these individual pieces of computer hardware and makes them easy and efficient to use. So let us start with the most fundamental hardware resource, that is the CPU, and see how does the operating system manage it. So let's get started. So let us start the discussion with this compute stack. As you can see, the operating system has to manage this layer of hardware, right? So before we talk about how the operating system manages any piece of computer hardware, if you see this stack, there is this hardware interface. The operating system has to work with the interface that the hardware has exposed to it. So before we can talk about how the operating system manages any piece of computer hardware, we have to understand how does the hardware interface look like for the operating system. So in the context of the CPU, we are going to first of all recall how does the hardware interface look like for the operating system, and then we are going to see how the operating system manages that piece of computer hardware, in this case the CPU, right? So let us look how does the CPU interface look like from the perspective of the operating system, right? So this is the CPU. We have studied about this in the first topic. There are two major components. The first is the storage part, that is the registers, and then there is the execution circuit, which has different units, for example the ALU or the control unit, right? So this is how the basic version of the CPU looks like. Now from the operating system's perspective, this execution circuit is not visible. What is visible is only these registers, right? So this is how the operating system views the CPU. So you can see here we have the operating system, and we are talking from the perspective of the operating system. So this is the hardware interface that the CPU exposes to the operating system. So as you can see, only the registers are visible to the operating system. The execution circuit is hidden to the operating system. Basically, the operating system can read or write these registers to communicate with the CPU, and it does not know how the underlying execution goes on, right? It doesn't even need to know, actually. It just needs to communicate with the CPU using these registers. So now that we have a good idea of how the interface of the CPU appears to the operating system, now let us see how the operating system manages the CPU. So let us now see how the operating system manages the CPU. So as we said in the previous video, in the context of the computer hardware, the operating system has two fundamental responsibilities or duties, you can say. The first is that it has to make sure that the hardware is easy to use. And for doing that, it provides abstractions on top of the physical hardware, right? And the second duty of the operating system is to ensure that the hardware is used efficiently. And for that, it does a careful resource management for that particular hardware resource. So now what we will do, we will talk in the context of the CPU and see how the operating system makes the CPU easy to use and at the same time ensures that the CPU is used efficiently. So let's start discussing how the operating system manages the CPU and performs its first role, that is making any piece of computer hardware easy to use. So let's see how the operating system makes the CPU easy to use. So the point is, if you talk about the early days of computing, and I mean 1960s or 70s, in those days of computing, a single computer system had only one single program running on it the entire time. So which means that that particular program that is inside the computer had the entire computer system and its hardware resources to use for itself, right? So this is how the scene used to look when in the early 1960s or 70s. But now the scenario is quite different. In the modern days of computing, we as users launch several different programs while using the computer system. To just illustrate this fact, let me give you an example. Let us say there is a student who is making a presentation for his school assignment. So let's talk about the different computer applications he might be using. So first of all, he has to use the PowerPoint application to make the slides. Then in order to look for information that he would be putting in the slides, he might be surfing through the internet, and for that he would be using the web browser, right? And apart from that, he might also be referring to a book. So for reading that book, he might be using the PDF reader application. And all in all, while doing all of these, he might be listening to some songs on the music player. So you see how the modern computer user launches several different computer applications while using the computer system. And this is very different from the early days of computing. In those days, there was only a single program that was running in the computer system at any point in time. But now the modern user will be launching several different computer applications while using the system. So we just discussed that in the modern era of computing, a normal computer user would be launching several different applications while using the system. And the fact is that in a modern computer system, there are several hundreds of computer applications running at the same time. So to give you an example, if you are using the Windows operating system, then you can open the task manager, and within the task manager, if you go to the performance tab, there you can go and check the CPU usage, and there you will also find the number of computer applications or programs that are running in your system. So at the time I took this screenshot, there were 241 programs that were running in my computer system, right? So if you see this term processes, so a process is a running program, and that is what is the title of this video as well. So we will talk about processes in great detail in the upcoming slides. So for now, the point is that in my computer system at that time, 241 programs were running, right? And let's check the number of CPUs. So the programs will be running on the CPUs. Let's check the number of CPUs. So in my system, there is one socket, and on that socket, the chip that is there has 8 cores. So it means I have 8 processors. So there are 241 programs running on 8 processors. So first of all, let's understand this number. How do we have so many hundreds of computer applications running in the computer system? A normal user would be launching few, like 5 to 10 programs at max, but hundreds of programs is quite a large number. Let's understand where is this number coming from. So let us talk a bit about why do we have so many computer applications in the system. So if you go to the task manager, there in the processes tab, you can get a breakdown about how many applications belong to which category, right? So as you can see, there are some apps and then there are some background processes. So basically, as I said, the normal user would be launching few applications only, right? Roughly 5 to 10 programs that would be running in the foreground with which the user will be directly interacting to get their work done. So these are the apps. As you can see, they are small in number. And apart from this, there are a lot of background processes which contribute to the large number of computer applications that we have in the system. So basically, the applications that you launch, they will have some subtasks that are not that do not require any user interaction or user interfacing. So these subtasks are basically launched as background processes, and the majority of applications that you see in the computer, they run in the background. These are background processes. And apart from them, we also have a large number of system services which are launched by the operating system itself. So these are services which do not require user interaction, but they are required for maintaining the system, keeping the system up, right? So there are several essential tasks or functionalities that these system services provide. So this is how we have so many applications in the computer system. Only a few of them are launched by the user. Rest of them are background processes or system services launched by the operating system. Nonetheless, the fact remains the same that we have a large number of computer programs running in the computer system. So the fact that we have a large number of computer applications is the system poses a problem. Why is it a challenge? Because the way the CPU has been designed, it can only run a single program at any given point in time. So that has the same has been shown in this picture. As you can see, there is a CPU and only one single program can run at any point in time. Multiple programs will be running at different time instants, but if you take any time instant, then at that time only one single program can run on the CPU. So if in my system there are 8 CPUs, then by the constraint of the CPU design, there can only be at max 8 programs running in my system. But that is obviously not the case, right? We saw that at the time I took the screenshot, there were 241 programs running on 8 CPUs. So how is it possible that so many programs are running on so limited number of CPUs? So let us understand this problem and see how the operating system tackles this issue. So let us understand how we can run so many programs on limited number of CPUs, right? So we saw that there was roughly 241 programs running on 8 CPUs in my system. So we want to understand how is it possible to run so many programs when we have when the number of CPUs that we have in the system is limited. So let me pose this as a problem. So the problem is, how do we run n programs on m CPUs where the number n is much greater than m, right? And let me reduce this problem, simplify this problem. So the problem that we want to solve is that how do we run n programs on one CPU? If we get the solution to this problem, then we can get the solution to the original problem, that is n programs m CPUs. So if you see, it's a fairly simple problem. There is one CPU and there are n programs. Whenever we have such a case, when there is one resource and there are multiple entities that want to use the resource, then the only way it is possible for all the entities to use the resource is that they will have to share the resource. So basically all these n programs have to share the single CPU, and then only can we run n programs on one CPU. So let us see how this will be possible with an example. So here we have a hypothetical example. Let's take a computer system where we have one CPU and n programs that want to run on it. So as we said, the only way that we can run n programs on one CPU is that all of these programs will have to share this single resource, that is the single CPU. So the way the sharing will happen, let's see how this sharing will happen. Let's assume program P1 is running on the CPU, right? This CPU resource is assigned to this program for some time, and after this program has executed few instructions, what will happen is that the control of the CPU will be taken away from the program. So the idea is that we will not allow any single program to run on the CPU for a very long time. We will only allow any program to run for a brief amount of time, and after that program has run for that brief amount of time, the control will be taken away and assigned to some other program. So as we can see, the control of the CPU will now be assigned to, let's say, the program n-1, that is the media player. So program 1, that was the web browser, ran for some amount of time. Then after that, the CPU was assigned to the media player. Again, this won't be allowed to run for a very long amount of time. The control will be taken away and then assigned to some other program. So let's say this time program P2, that is the word processor, is allowed to run, right? So in this way, by assigning the CPU to any program for a brief amount of time and letting it execute instructions, this is how we are able to share the CPU by frequently switching the control of the CPU between different programs. So after program P2, let's say we assign the CPU again to program P1. So this is how, by sharing the CPU, all these programs can make progress. Basically, the single resource that we have, we are switching its control frequently between the different programs in the system, and that is how we are able to run multiple programs on this single CPU. This idea is called time sharing, because if you see, we are sharing the CPU time. The CPU time is being shared between all the programs in the system, and this idea, that is why it's called time sharing. So we have the answer to our problem: how can we run so many programs on few CPUs? That is, we will use the concept of time sharing. So now let us see some more points about time sharing and understand it in more detail. So now we know how we can run multiple programs when we have a limited number of CPUs in the system, and that is by the concept of time sharing. But another question, a very important question needs to be answered, is that who will implement this time sharing? Because if you see the programs, the way we write programs, when we are writing programs, we assume that the CPU will always be available for our programs. We don't assume that control of the CPU will be taken from our program. So, right, someone else, some third party, some intermediary has to ensure that this time sharing is implemented. The control of the CPU has to be frequently switched between different programs. And as you might have guessed, that someone is the operating system. So within a computer, we have so many programs that are running, right? And we have limited number of CPUs, and it is the responsibility of the operating system to ensure that the CPU is time shared between all the different programs, so that every program gets to execute on the CPU and make progress. So as you can see, it's a very important responsibility on the operating system to implement this time sharing. And in order to implement this time sharing, the operating system must be aware of all the running programs in the system. So as you can see, in this system, there are n programs that want to run. So the operating system must have the knowledge, or it must keep track of all these running programs. And this concept of running program is what is known as a process. So a process is an abstraction to manage the physical resource, that is the CPU. That is why the title of this video is process. By keeping track of all these running programs and modeling them as a process, the operating system is able to implement this time sharing. So let us take one more example and see how the operating system keeps track of all the processes and implements the time sharing in the computer system. So this is very crucial, because as we saw, because that there are multiple programs that are there in the system, and number of CPUs is limited. So this implementation of time sharing is very crucial, and that the operating system does by modeling the running programs as a process and switching the CPU between them. So now let us take an example and see how the operating system implements the time sharing of CPU between different processes. So here we have a hypothetical computer system. There are three processes in this computer. This is the single CPU, and now it is the responsibility of the operating system to keep track of all the processes and ensure that they are allocated the CPU. So let us see how does the operating system accomplish this time sharing. So first of all, it has to make a selection between all the processes that are there, P1, P2 and P3. It has to make a selection as to which process should the CPU be assigned. So let us assume the operating system selects P1 on some criteria, and it allows the process to run on the CPU for some amount of time. After it has executed some instructions, now the operating system has to pause this process and make another selection. This time, let's say it selects process P2 and allocates the CPU to this process. In the same way, it has to frequently pause the processes and switch the control of the CPU between different processes. It has to keep making selections so that every process in the system is allocated the CPU at some point and is able to make progress or execute instructions. So let's say now process P3 is selected, then after some time the control is given to P2, then let's say again it is given to P3, and finally operating system allows process P1 to run. So you can see how the CPU time on this axis is literally shared by the different processes P1, P2 and P3, and how all of these processes execute on the CPU at some point in time. They're able to execute instructions not for the entire duration, but they're able to share the CPU and make progress. So this is how the operating system keeps track of all the processes and allocates the CPU between them so that they can execute their instructions and make progress. This is how the time sharing is implemented by the operating system. So let's talk about a very important point related to time sharing. So this is the computer system. There are different processes in it, and the operating system ensures that the control of the CPU is allocated to each of the process at some point in time. So all the processes in the system get to execute instructions and make progress, right? And when that particular program is running on the CPU, then it is the only program on the CPU. So this gives the illusion to each of the programs that the CPU is private to them, although there is only one single CPU in reality. But since all the programs are allocated the CPU by the operating system, and when they are using the CPU, they are the only program on the CPU. So it gives an illusion to all the programs that the CPU is private to them. They have a private CPU. So this is how it looks like. Basically, it's an illusion. Obviously, it's an illusion created due to time sharing. There is only one single CPU, physical CPU, that is shared by all the programs. But since the operating system is constantly or frequently switching the control of the CPU to each program, and each process while it is running, it's the only process on the CPU. Every process in the system is given the illusion that they have a private CPU. So basically, if you see closely what the operating system has done, it has taken one physical resource and it has transformed it into as many virtual resources as the number of programs. So in this case, there is one physical CPU, but essentially there is an illusion of n virtual CPUs. So these CPUs are obviously an illusion, that there is, in reality, the CPU is not private to any particular process. It's just a shared resource. But by time sharing the CPU in this fashion, the operating system has virtualized this resource. So this concept is called virtualization of CPU, where every process thinks that the CPU is private to them. So this is an important consequence of time sharing. So if you look closely at this concept of virtualization of CPU, any program that you launch, the operating system keeps track of that running program. It models it as a process and it will be allocated the CPU. And that process will be given the illusion that it has a private CPU in the system. Although there is only one single CPU, physical CPU in this particular example, but as you launch more programs, they will be modeled by the operating system as a process and they will be allocated the CPU. All the processes that will be there, they will be given this illusion of a private CPU. So this is what makes the CPU easy to use. As a user, now we don't have to worry about whether there are enough CPUs in the system or not. We can launch as many programs as we want, and the operating system will guarantee that the CPU is allocated to each of the programs. So this is how the operating system makes the CPU easy to use. It gives the liberty to the user to launch as many programs as they want, and it will guarantee that all of the programs that the users launch, they will be allocated the CPU, right? So this is how the operating system fulfills its first fundamental duty in the context of the CPU, that is making it easy to use by providing the abstraction of a process that is a running program, right? Whenever we want to use the CPU, we just have to launch a program. That program, when it starts running, it becomes a process and the operating system ensures that the CPU is allocated to it. So this makes the CPU very easy to use for us as a user, and it is accomplished by the operating system. So now let us look at how the operating system fulfills its second fundamental role, that is making sure that the hardware is used efficiently in the context of the CPU. So now we'll see how the operating system does a careful resource management. Here the resource is the CPU, and make sure that it is used in an efficient manner. So this is the compute stack, and if you talk about the hardware layer, then the CPU is the most fundamental and basic hardware resource in the computer system. It is required by all the user applications for the execution of instructions. So all the user applications need the CPU to make progress and execute instructions, right? So it's a resource that is shared and needed by all the user applications. Also, it is limited in nature, that is, the CPU does not offer unlimited compute power. It has to be used in a careful manner, and that is where the operating system has to allocate this shared resource to all the user applications in a proper way. So let us see how the operating system does a careful resource allocation when it comes to the CPU. So the problem of allocating the CPU to the different processes in the system has been given a proper term, that is called CPU scheduling. So basically in CPU scheduling, the role of the operating system is to select the next process that has to be assigned the CPU. So as you can see, when processes are executing on the CPU, there comes a time when the operating system has to decide that now we should pause the current process, and after pausing the current process, the next process that will be allocated to the CPU, that also has to be selected. So all of these decisions, when to pause the process, after pausing which process to allocate the CPU, come under the term that is called CPU scheduling. Basically, if you see this term, we are scheduling the CPU for usage between the different processes. The operating system is deciding when the CPU will be used by different processes. That is why it's called CPU scheduling. So let us now see what are the different factors that the operating system has to keep in mind when scheduling the different processes in the computer. So one of the most basic requirements that the operating system has to keep in mind when scheduling the CPU is to ensure that the CPU is allocated to all the processes in a system. So there are several processes in the system, and no process should starve, or basically it should not be the case that a particular process is being deprived of the CPU. Then it won't be able to execute its instructions and make progress. So this is something that we do not want. So when the operating system is allocating the CPU, it has to make sure that all the processes in the system are given a chance, a shot to execute on the CPU, right? So in the previous slide, we said that all the processes in the system should be given a chance to execute the CPU. So we were talking about being fair, but this does not mean that all the processes in the system have a equal priority. Not all processes are that important to the user. So for example, the programs that the user personally launches to get some work done, with which they directly interact, they are more important than some background processes. So this factor the operating system has to keep in mind when selecting the next process that has to be given the CPU. It has to give more priority to processes which are important from the perspective of the user. So those processes that are running in the foreground, they determine the user experience. If they are not allocated the CPU in a timely manner, then the user experience will deteriorate. So this the operating system has to keep in mind and prioritize some processes over other depending on their importance. So the next point talks about the fact that in a modern computer system, there is not just one single CPU, there are more than one CPUs, right? There are multiple CPUs. So we saw that in my case, in the screenshot that I showed you, there was 241 programs in the system that had to be run on 8 CPUs. So now how should the operating system allocate or distribute this load of processes among the different cores? So this is also an important thing. So the operating system has to carefully and evenly distribute this process so that all the processes are able to execute and the load on the CPUs or the different cores is also properly balanced. So these are some of the things that the operating system has to take care when doing CPU scheduling. So another very important point when it comes to time sharing is the overhead that it takes to switch from one process to another. So basically, if you see this diagram, the operating system is frequently switching the control of the CPU from one process to another. And this switching between processes is called context switch, right? When there is a context switch, then the operating system has to pause the current process. It has to save some state so that when the time comes to resume this process, it can restore and resume it from the exact point where it was paused, right? So this context switch takes some time and there is some overhead associated with it. And this has to be minimized, right? So as you can see, there are several context switches in this diagram. And if there are more context switching and the context switching is costly, then that deteriorates the performance of the system, because when the process is executing, that is something useful. But when we are doing context switch, that is pure overhead. So the operating system has to make sure that the number of context switches is in a fair limit, and the overhead that is incurred during the context switch, that is also minimized. This is very important for the performance of the system. The final point that I want to talk about is that while doing all of this CPU scheduling, the operating system has to make sure that the CPU is always busy. That is, the resource utilization is high, right? So CPU time is a very important resource and it has to be used in a meaningful way. So the choices that the operating system takes in terms of which process has to be assigned the CPU next plays a very important role in determining the CPU utilization. So there are times when the program is running and it has to wait for some event, and when it is waiting, it is not doing any useful work. So in those scenarios, the operating system should take the control of the CPU from those processes which are waiting for some event and assign it to other processes which want to execute, which are ready to execute. So all of these decisions basically affect the utilization, and it is the responsibility of the operating system to make sure that it selects the processes wisely and ensures that the utilization of CPU is high. So in the previous slides, we saw different things that the operating system has to keep in mind when doing a resource allocation of the CPU to the different processes. So these are the things that come under resource management. So when the operating system is trying to make sure that the CPU is used efficiently, these are the points that it has to keep in mind when doing the resource management. So in the context of CPU, we saw that the operating system has to be fair in its allocation to the different processes. At times it has to prioritize some processes over another. Then it has to make sure that the context switch overhead is minimal, the resource utilization is high. So all of these things come under resource management, and the operating system does all of this to make sure that the CPU is used in an efficient manner. So guys, this was it for this video. In this video, we saw how the operating system manages the CPU, how it fulfills its two fundamental responsibilities in the context of CPU, how it makes the CPU easy to use by providing the useful abstraction of a process. By doing time sharing of the CPU between different processes, it makes the CPU very easy to use. And we also saw what are the different things that the operating system has to do while managing the CPU as a resource, so that the CPU is used in an efficient manner. So this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.